Hello, thank you for attending my presentation today. My name is Kevin Heppner, and I'm going to be talking today about how to go about modeling a solvent extraction circuit for uranium, including the control of molybdenum. We're going to be using a thermodynamic modeling approach to model a solvent extraction circuit. An overview of my presentation today, we're going to talk about what a process model is. We're going to look at how thermodynamic modeling is used and how it is used in application to solvent extraction. Then we're going to look in particular at the uranium and molybdenum solvent extraction chemistry. Then we're going to look at how we used literature data, so data available in the literature for uranium and molybdenum isotherms, to fit the data to that chemistry to calculate the equilibrium constants for various reactions. Then we're going to look at how we used this data to simulate a typical uranium solvent extraction circuit with molybdenum in the feed in a baseline simulation for typical operating conditions. Then we're going to look at a sensitivity analysis or deviation from those baselines to look at how the model responds. And then we're going to summarize at the end. So this is an overview of the SysCAD model. So SysCAD is one of many available simulation packages, but we'll be talking about that today. We're going to look at starting how it can be used throughout the cycle of a project, going from feasibility all the way through to plant expansion. I'm not going to go into detail here, but basically modeling techniques are used throughout the life cycle of a project and operation. Within SysCAD, we have the ability to call out several different thermodynamic calculation engine packages. So these are detailed thermodynamic calculation packages that do very complex analysis to calculate things like phase equilibrium, pH, and the like. These detailed thermodynamics can be applied as needed within a package. And within a single SysCAD model, you can have multiple of these thermodynamic calculation engines with multiple chemistry models for each. It incorporates parallel processing for computational efficiency, and there's many useful user-friendly features. So now let's talk about what we're going to actually do today. We're going to look at the solvent extraction process. For those that aren't familiar with solvent extraction, I'm going to go over quickly what a solvent extraction cell is. This is a solvent extraction cell. On the far left-hand side with the mixer, you have the mixing chamber. In this, you have the mixing of organic and aqueous. They are mixed intimately over a period of approximately 3 minutes or so, and they hopefully come to equilibrium. The formed emulsion then overflows a weir from the mixer and goes into a settling chamber. In the settling chamber, you have weirs that control the separation at the end of the liquid from the lighter organic phase. And there are often coalescer plates within or different mechanisms in there to promote separation. That's what a solvent extraction cell is. And when we mention a solvent extraction circuit, it's a collection of these cells used for different purposes, with the organic being a recirculating fluid through all of them. The solvent extraction modeling, if we compare different approaches that you can use, you can do things like define reaction extents. So here you would just define the reactions that are occurring and you specify their extents. And this is very useful for preliminary analysis. Next, you have isotherms, which are commonly used in plant conditions. You can generate plant isotherms using your production liquor and your organic. And this is useful to understand your behavior, but it does not apply when you have significant changes in operating conditions. Then you have a thermodynamic approach. What you do with this is you generate pure system isotherms for each component. So every single component, like you would look at uranyl sulfate, molybdate, different types of things that you're extracting, each with fresh organic. The advantage with doing this is then you have a very pure system that you can write a very detailed thermodynamic model for, where you're only unknown is the free energy of the organic species. So then when you calculate the free energy of these organic species, you can now put them together in a combined model where you will get a prediction of competitive extraction over a wide operating range. So the workflow we're going to use today, you start with pure system isotherm data. We've obtained this from literature. You fit it to a thermodynamic model, and then you use the fitted model for process optimization and design. First, we're going to talk about fitting the data. So this is the uranium extraction chemistry to the tertiary amine. There's a number of reactions here. I won't go into them in detail, but it basically involves two steps. First of all, you need to acidify the amine. Think of acid like the glue. So you have to acidify it so that it becomes positively charged and therefore it can react with anions. Now, the extraction equilibrium of uranium then takes the sulfate anions of uranium. It's known to form uranyl disulfate and trisulfate anions, and it reacts with the acidified amine to form these organic uranyl sulfate salts. For each of these 4 reactions, you have to calculate the log K value via data fitting. So you need an isotherm to be able to do that. And in this case, the data was obtained from the reference below, Yakubu and Dudney, in 1987. Now, if we look at molybdate extraction, again, molybdate requires, because molybdate is an anion, it again requires an acidified amine to be able to extract to it. So in this case, some of the acidified amine then, in competition with the uranium, is used to extract molybdate, and you form similar molybdate salts. Now, one thing to note is that other polymer ions are known to exist, but due to the availability of data, they're not included in this model. We took a simple approach because of the number of data points we had. Remember that every reaction is like an additional parameter in a polynomial. So as you add more reactions, you need more data to have confidence in those parameters. So to have confidence in the model, we kept the model very simple. And the data that we used in the isotherm was from Koka et al. In 1990. Now, for strong acid stripping, the model that we used, strong acid stripping was outside of the limits of concentration for the model. So for this particular model, we used an isotherm. So we used a literature isotherm published by Moraes et al. In 2005. And this particular reaction, it strips the organic salt by forming an acid uranyl sulfate complex in solution. So you can see the reaction there over the 2 forms of uranium. When uranium is extracted, it can form an either a 2-to-1 amine to uranium complex or a 4-to-1 amine to uranium complex, depending upon the ratio of amine to uranium in your extraction conditions. Now we look at the wash cell chemistry. The wash cell chemistry is actually very similar to extraction. And the reason for that, and we're going to talk about it a bit when we show the process flow diagram, is that in the wash cell, you add water to the organic that came off stripping, which has a lot of acid in it. When you do that, then it extracts some acid, and the aqueous is very similar to the aqueous seen in extraction. And for this reason, then, you end up with any entrainment of strip 1 liquor, which will contain some uranium. This will directly impact uranium loss, because what will happen is that any uranium that's in the aqueous will then be extracted to the organic in that mixer. So this is something to consider and something we'll talk about in a bit. Finally, regeneration cell chemistry. So the regeneration cell takes the washed organic, and it is modeled using a series of reactions with 100% conversion. So in this, we also use a side calculation. So a side calculation essentially looks at a stream in SysCAD and calculates the pH based upon the thermodynamic model being used. So think of it like a pH transmitter. And in here, we have a general form of reaction equations where the anion could be uranyl sulfate, molybdate, or sulfate. And so we just have it there. So we have an acidified amine complex plus sodium carbonate gives the unacidified amine plus sodium bicarbonate and as the sodium form of the anion as a salt. So now we look at how we did the data fitting. When we did data fitting, what we did is we generated a very simple model. You can see it there. We basically have a single stage with a known feed, and we use the thermodynamic model in there. So what you're really simulating is a shakeout test where you take a known aqueous and a known organic, and you mix them together in a beaker, and you let it go until you reach equilibrium, and then you measure the results. So with this, we get a number of points on an equilibrium line, and we can use that to calculate the log K values for extraction reactions. What we did is we used the SysCAD Python interface. So where SysCAD can be controlled remotely from Python, and we adjusted the log K values iteratively using the SciPy Optimise package. So Python repeatedly runs SysCAD until the function is minimized, where the function is the difference between the predicted and experimental values. And these are the results. You can see good results for data fitting for sulfuric acid. Here we have organic over aqueous distribution coefficient as a function of pH. Here again, as a function of pH, we have the distribution of uranium in the organic and aqueous. Again, it's a good data fit. And then here for molybdenum, we've shown it as a concentration of molybdenum in the organic, both predicted and experimental. And you can see that it closely follows a line of the parity plot. So it's a good fit to the parity plot. So all of those data fitting were successful. So we had a good fit of uranium, acid, and molybdenum extraction to the organic. So after fitting the data, then we're going to use the fitted model for process design and optimization. So let's have a look how we did this. So we started by building a model of the extraction and scrubbing circuit. So in this particular case, we have 4 extraction circuits. So we have pregnant solution, which will typically come from the overflow of a countercurrent decantation circuit. The pregnant solution then flows in the downward direction, going from extraction cell 1 to extraction cell 4, and it goes through. At extraction 4, you provide barren organic, which is coming from the stripping and regeneration circuit, and it goes from cell 4 to cell 1, so they move countercurrently. What happens is the pregnant solution is removed, has its dissolved metals removed, all the anions, such as uranium, molybdenum. You don't want to extract all the molybdenum, but oftentimes that happens, or most of it anyways. The pregnant solution becomes raffinate, and the raffinate goes on to water treatment. And the other product out of extraction cell 1 is the loaded organic. The loaded organic is then scrubbed with a dilute acid solution to remove some unwanted metals such as arsenic. Arsenic is not included in this model, but these are typically referred to as an arsenic scrub cell. And so these scrub solutions, then they recycle this stream back, and then the loaded organic goes on for processing and stripping. So the uranium balance is that the uranium in preg solution should be essentially equal to the uranium in the loaded organic, because typically you get very, very high extraction efficiencies. Next, we look at the stripping, washing, and regeneration circuits. So in this particular case, we have 7 stripping cells that we used. Now, in this case, now the loaded organic is introduced at strip cell 7, and it moves up the page to strip cell 1. And as it goes through, it is contacted with strip solution. The strip solution on the other side is introduced at strip cell 1 and goes down. It is a mixture essentially of strong acid In this case, we're looking at strong acid stripping. Other stripping technologies include ammonia stripping, as well as other types have been tried, such as sodium salts. Anyways, so we go down, and at the end, then the loaded strip comes out, and the loaded strip should contain most of the uranium. Then what happens is the strip organic comes out, and it is then split between washing and regeneration or barren organic. So it is either sent to the wash cell or it is sent to the barren organic tank. The portion that is regenerated goes through washing, and the wash water is added. So as I mentioned before, this creates conditions that are very amenable, or very similar to extraction, because you add wash water with the organic, which contains lots of acids. You end up with a dilute acid in the aqueous. And so any entrained uranium in the organic, such as like any entrained aqueous, will, when it hits the wash cell with wash water, will be re-extracted onto the organic, which will then go to the regeneration cell. In the regeneration cell, we add sodium carbonate to fully neutralize and remove all dissolved salts from the organic by getting rid of the acid. Remember, the acid is the glue. So once you kill the acid, then the amine doesn't want to attach to anything anymore. That's what you end up with is a scrub aqueous solution, which is high in contaminants, and a fresh organic solution coming out, which combines with the barren organic, and it goes back around. So the regeneration cell is the main source of removal of contaminants from the circuit. Raffinate also does to some extent, depending on how you're running extraction. I would like to note that here you can see the output from one of the thermodynamic calculations. In this case, we are using the PHREEQC interface, and you can see the aqueous and the exchange, which is the organic calculations there, which are the results of a thermodynamic calculation. So for this model, we looked at the following input parameters. I'm not going to go into them in detail, but they represent typical operating conditions. Okay, they're not based on any plant, but they just show typical general operating conditions that you might have for this kind of condition. So you can see them here. From the results of this simulation, we can see we have calculated certain things. So we have the concentration of the moly in the barren organic and the uranium in the barren organic. So there's a little bit of residual uranium that's left. Remember, some of that is due to the re-extraction in the wash cell, and some of it is due to incomplete stripping. We have the loaded strip U3O8, 130 grams a liter, which is quite typical. And the loaded strip flow, which is based on the O to A ratio that you set up in your stripping circuit. And then we also calculate things like reagent usage, U3O8 recovery. Key thing to note is that the U3O8 losses in regeneration are predicted to be much higher than that in raffinate, which is expected. Just some general observations that we made on the baseline simulation. The majority of extraction of uranium was completed after a single stage or two. Stripping work in the strip circuit was much more evenly distributed across the cells, although we saw more uranium stripped at the end receiving loaded organic. So these are both expected results. As well, wash cell conditions, as I mentioned, are similar to extraction. Therefore, we could see a strong trend between entrained stripping aqueous and the amount of organic, or the entrained strip aqueous and the loss to regeneration. You saw a strong trend between the two. After we did this, we looked at some operational parameter sensitivity analysis. You can see it here. So we have our base case repeated, and then we looked at different cases, such as a decrease in head grade, a reduction in the number of strip cells that we used, a change in the O to A ratio of the strip flow, or in the strip circuit, and a change in the molybdenum head grade in the PHREEQC solution. So the head grade is both the concentration in the solution, in the pregnant solution. So you can see here, as you expect, U3O8 head grade causes a drop in loaded strip U3O8, an increase in sodium carbonate usage per kilogram U3O8, simply because of the fact that you have less uranium coming through, and similar effect on acid. So it's really due to the fact you have a smaller denominator in the KPI for reagent usage. And the regeneration U3O8 loss is also dropped. Okay. In the strip cells going from 7 to 6, you can see an increase in the uranium losses to regeneration, which is expected. And you really no other major changes to the process. In the strip flow, going from a 20 to 15 O/A ratio, which means we're essentially increasing the strip flow, the strip solution flow, you see an increase in acid usage as you would expect, and you see a drop in the loaded strip concentration. The regeneration U3O8 losses drop considerably, so you do a better job of stripping, and this then results in a slightly lower usage of sodium carbonate. Finally, the molybdenum head grade going from 50 to 100 milligrams a liter. What we did here as well is we also doubled the amount of regeneration. So not only, so when the molybdenum head grade goes up, then you have to increase the amount of regeneration you do. So we went from 10% to 20%. So similar results for barren organic molybdenum, which is what we were going for. Loaded strip is about the same, but the U3O8 losses and regeneration doubled because we essentially had to regenerate more. So it shows the effect that when you have higher molybdenum, it can cause issues for your efficiency. Finally, in conclusions, we can see that elevated molybdenum in PHREEQC feed will have a significant detrimental effect on the overall process in terms of uranium recovery. Organic regeneration is a major source of uranium loss, and we've demonstrated that. What we see as well, the wash cell, although it recovers acid, it also promotes extraction of uranium to barren organic. And we've used a combination of first principles thermodynamic models and empirical models within a SysCAD model and successfully applied them to be able to model the system. A little bit further, we can use different types of test work data. It can be used a variety of purposes, depending on the stage of project you're at and the information you have. You can use thermodynamic calculations seamlessly embedded in a SysCAD flowsheet, and no user input reactions are required. It's based on free energy minimization. And depending on where you are in the project, you can use different levels of accuracy. You can increase your model accuracy as you go. One thing about it is that you can take metallurgical test work data, such as that isotherm, and put it directly into your model as a storage for process knowledge. And it's important to recognize that the first principles model that we developed has a wide applicability range. So that's a key advantage of that approach. With that, I thank you for watching my presentation today, and I am open to questions.